A feature of rational functions are vertical and horizontal asymptotes. So the vertical asymptotes are going to occur where our function is undefined. And then the horizontal asymptotes come from, we're going to have some different rules that we'll look at down here for what determines what the horizontal asymptote is. But this horizontal asymptote links to end behavior. It's like what our function does in the long run as x goes out to positive infinity and x goes out to negative infinity. And then vertical asymptotes are where our function's undefined, and this is a short run behavior. This is going to be kind of a focus at the middle of our graph and basically where our function can't cross over. So with rational functions, the general form for rational functions, let's call it r of x, is equal to p of x over q of x. Use this general form, and the idea is that we have some function in the numerator, some function in the denominator. And it's the fact that we have something in a denominator, that's where our vertical asymptotes comes in, because we cannot divide by 0. So our function is going to be limited in some way. So let's start by looking at some basic graphs of our functions 1 over x and 1 over x squared. And what we can do is, let's actually talk about this in terms of a table of values. So let's say I choose some values for x, and I choose some values for y. And I'm going to choose x values. How about -2, -1? I'm also going to look at -1/2, 0, 1/2, 1, 2. So I'm focusing really on the middle of this graph here. So at -2, if I plug in -2 into the denominator there, I'm going to have a -1/2. If I plug in -1, 1 divided by -1 is -1. If I plug in -1/2, let's get some review of our complex numbers here. If I have -1/2, what I could do to simplify is I could multiply both the numerator and denominator by 2, so that in that denominator, those 2's cancel. So what I would have is 1 times 2 in the numerator divided by -1, which is -2. This 1 over x is also called the reciprocal function, because what it's doing is it's taking the number that's given to us and flipping the numerator and denominator. So if I have -1/2, that turns into -2 over 1. If we plug in 0, we're going to run into issues because we cannot plug in 0. So that's going to be does not exist. If I plug in 1/2, that's going to be a +2. If I plug in 1, that's going to be +1. If I plug in 2, 1/2. So let's start plotting these points here. So -2, -1/2, -1, -1, and -1/2, -2. And then same thing, and then 0 is undefined, and that is where our vertical asymptote is. So I'm going to draw this line at x equals 0 that goes vertically, because that is our vertical asymptote, would be described as x equals 0, since it's a vertical line. All right, and our other points, let's see, +1/2, +2, +1, 1, and then 2, 1/2. All right, so let's talk about getting other points for this and just kind of talking about the trend that occurs here. So let's focus around our our vertical asymptote there. So our vertical asymptote, as we get closer and closer to it, so like we looked at +1/2, if we plugged in +1/4, we'd be getting +4. If I plugged in +1/6, I'd be getting +6. So what's happening is as x is getting closer and closer to 0 there, our y values are growing and growing. So if I go to the extreme of like plugging in +1/100th, the output would be 100. So there's this relationship of if we plug in something very small, the output is something very large. And this connects to what I put down below here with this large small principle, is coming from this fact that we're taking 1 divided by, and then we're plugging in something that is super small in the denominator. So like 1/100th, 1/10th. So plugging in a teeny tiny fraction into that denominator. So let me even write that out of it looking like 1 over 100. So that 1/100th is captured in that denominator. The output that we get is something very large because of this reciprocal relationship. So I'm going to have here is, if I'm focusing close to that x equals 0 on this right hand side, we're going up and off to positive infinity there. So we're going to be coming down, and then we'll connect with those 3 points that I graphed. But then let's talk about what happens when we plug in something really big. What if we plugged in something like positive 100? Or let's not go quite there yet. If I plug in 4, we're going to be at a 4th. If I plug in 6, we're going to be at 1/6. So when I plug in something large into the denominator, so if I hop down here, like if I plugged in 1 over 100, so I'm plugging in 1 over something that is very large, the output is something that is very small. So that's this reciprocal relationship that we're seeing, where it switches behavior based on input and output. So the idea being, we're getting teeny tiny fractions out as we go out to positive infinity with x. So what's happening is our function is going to be getting closer and closer to 0. It's going to get infinitely close to 0, but never equal 0. And that's our horizontal asymptote there. It's the idea that in the long run, our function is going to get very close to 0, but never actually equal 0. So what we're seeing here is a horizontal asymptote. So I'm going to draw this line here horizontally. So it's a horizontal asymptote at y equals 0. So that horizontal line of y equals 0, that's where our function's approaching in the long run. Now I focused on this positive side, but the same thing is happening down here on the negative side. So like if we plugged in negative 100, we'd be getting negative 1/100th. So again, infinitely close to 0, it's just on the negative side, so it's underneath the x-axis. So on the left-hand side of our graph, we're coming from very close to 0, and then we're going to connect with our little 3 dots that we graphed already. And then in the long run, or sorry, in the short run, as we get closer and closer to this vertical asymptote, what's going to happen is we're plugging in teeny tiny fractions that are negative, which means we're getting very big negative numbers. So if I plug in negative 1/100th, we're getting negative 100 out. So this is going to go off to negative infinity. So reading from left to right on our graph, where we have this vertical asymptote that we can't cross at x equals 0, we have this horizontal asymptote at y equals 0. What's happening is, so from the left-hand side, we're coming from just below 0, and then our function connects with those coordinates, what, -2, -1/2, -1, -1/2, -2, and then it goes off to negative infinity as we get closer and closer to that x equals 0, but we can't equal x equals 0. So we have this line we can't cross at x equals 0, and then just to the right of x equals 0, we're coming from positive infinity. So you come down from positive infinity, connect with those 3 coordinates, 1/2, 1/1, 2/2, and then in the long run, our function approaches 0 from above since we're using positive values, and in the long run, our function's just getting closer and closer to 0 from that horizontal asymptote. All right, so just to see how things change a little bit when we square x in the denominator, so we're going to look at f of x equals 1 over x squared, but a lot of the behaviors are going to stay true here. But let's look at that kind of same table of values, so x and y. Let's look at -2, -1, -1/2, 0, 1/2, 1, 2. All right, so again, when we're plugging in here, make sure you're thinking about parentheses. So this is 1 over x squared, so it's like 1 over and then empty parentheses squared, and we're plugging in our x values into those parentheses. So if I plug in -2, that'll be a +4. So we are graphing 1/4 when we're at x equals -2. If I plug in -1, that'll all simplify to a +1. -1/2 will turn into a 1/4. 1 divided by a 4th is 4. Plug in 0, we can't do that. If 0 squared is 0, and we can't divide by 0, so that does not exist. So we're going to be seeing a vertical asymptote at x equals 0 again. And then if we plug in +1/2, we'll be getting +4. Plug in +1, +1. Plug in +2, 1/4. So let's graph these. So -2, 1/4 is about right there. -1, 1. And then -1/2, +4 is about right there. And then actually we're going to have some nice symmetry on the other side of the graph too, like that. Okay, so in terms of behavior, that small and large principle still holds, where if I'm plugging in these really big numbers to the negative side and positive side, it's like that extreme of -100. What, that's going to be a 1/1000th? That's going to be teeny tiny. Ooh, even more than that. What, that would have 4 zeros? Yeah, 10,000. So with that, something that's teeny tiny, but will be positive. So we'll be just above the x-axis, and then we'll approach and connect with those 3 points that we just connected, and then we'll go off to positive infinity. So we're going to come from about 0, connect with that 1/4, 1, and 4, and then as we get closer and closer to that vertical asymptote, we're going off to positive infinity. And then we're going to see the same thing on the right-hand side of the graph. So next to the asymptote, we're coming from positive infinity, because those really large values, by plugging in those teeny tiny fractions. And then we're going to connect the dots. And then in the long run, we're going to be getting closer and closer to 0. So we have that horizontal asymptote at y equals 0 for this graph as well. So those are our 2 basic functions, the reciprocal function and then our 1 over x squared function, to just see how the behavior looks with those asymptotes in there, and the kind of short run and long run behavior of our graphs. All right, so we talked about that large-small principle, which is really bringing through the idea of what happens near the vertical asymptote when you're plugging in really small values, and then what's happening with the horizontal asymptote as you're plugging in really large values. But basically, in this case where we're plugging in really small values, that's going to be very close to the vertical asymptote, so that's like our short-run behavior. And then this scenario where we're plugging in really large values, that's our long-run behavior. Okay, so as we see, vertical asymptotes are going to occur where we take our rational function, and it's going to be undefined, where that denominator function q of x is equal to 0. So this next example, we're going to find all the vertical and horizontal asymptotes. We haven't quite talked about how to find the horizontal asymptotes yet, so we're going to put that on hold, but let's focus on finding the vertical asymptotes for these 3 functions here. So if we have 2x over x plus 1, if I want to find the vertical asymptote, then what I'm going to do is take that denominator of x plus 1 and see where does it equal 0. So I'm going to subtract 1 from both sides. So x equals -1. So that right there would be our vertical line that our function cannot cross. So there's our vertical asymptote. I'm just going to separate this because then we'll look at horizontal asymptotes next. All right, our second function, this x plus 2 over x squared minus 1, finding the vertical asymptote. I'm going to take x squared minus 1 and see where does that equal 0. Two ways to go about this. You can either factor or use the square root method. I'm going to go ahead with the square root method. So I'm going to add 1 to both sides. And then take the square root of both sides. And when we do that, we get plus or minus. So I'm going to have x equals plus or minus the square root of 1, which is just 1. So this has two vertical asymptotes, one at positive 1 and one at negative 1. And then our last function here, x squared minus 3 over 2x plus 1. So for the vertical asymptote, I'm going to look at 2x plus 1, and where does that equal 0? Subtract 1 from both sides, so 2x equals negative 1. Divide both sides by 2, x equals a negative 1/2, and that would be our vertical asymptote. So notice with those, I didn't do anything with the numerator function. You can just completely ignore it because it's all about where does the denominator equal 0 for those vertical asymptotes. All right, let's talk about how we find our horizontal asymptotes. And what it's going to come down to is a comparison of degrees of the numerator and denominator. So we have some function p of x divided by q of x for our rational function. So these are two polynomials here. So what's going to happen is we're going to look at the degree of each of those polynomials. So when we look at p of x, we're going to say n is the degree of that polynomial. So that's the degree of the numerator. So we're looking at our exponents and looking for what's the largest exponent. Q of x from the denominator, we're going to use the letter d to represent the degree of the denominator. So whatever polynomial is down there, we're going to look at that degree. So when we do a comparison, there's three scenarios. Either the degree of the numerator is larger than the denominator, or the degree of the numerator is smaller than the degree of the denominator, or they're the same. And for each of those three scenarios, there's going to be a different behavior for the horizontal asymptote. So let's go through these three cases. If the degree of the numerator is larger than the degree of the denominator, for our purposes, we're saying, there's no horizontal asymptote. That is true. No horizontal asymptote. What is actually happening is there's an asymptote that is slanted, or we also call it oblique. So we could find like an equation of a line. We're not going to worry about that. So for our purposes, if we're looking and the degree of the numerator is larger than the denominator, we're just going to state that there's no horizontal asymptote. When the degree of the numerator is smaller than the denominator, our horizontal asymptote is y equals 0. And that's exactly the case that we saw with our basic functions up above with 1 over x and 1 over x squared. Look at how the degree of the numerator is 0 for both of these cases. Because having just a value of 1 in the numerator, that doesn't have any degree. But then for, let's see, 1 over x, the degree of the denominator is 1 for when we have 1 over x, because that x has an exponent of 1. So comparing 0 and 1, that denominator is larger. So that's why we're seeing y equals 0 come through. It's also true for the 1 over x squared. The degree of the denominator is a positive 2. So the degree of the denominator is larger, and that's where we're seeing that y equals 0 horizontal asymptote. So we already saw some of those cases. And now the last one. When the degrees are the same. What we're going to use for notation is I'm going to describe it as, so it's a horizontal line, y equals, and then we're going to say a over b. So where are a and b coming from? A is the leading coefficient in the numerator. So a is the leading coefficient of p of x. And then b is the leading coefficient of q of x. So it's going to be a ratio of two numbers, and it's the ratio of the leading coefficients. So let's go ahead through this and we'll look at a comparison of how these all come through. So let's go back to that example where I said we were putting on hold those horizontal asymptotes, and let's go through. So our first function, the 2x over x plus 1, so the degree in the numerator is 1. The degree in the denominator is also 1. So this is a case where, let's see, I'm looking for the horizontal asymptote, and the degree of the numerator is equal to the degree of the denominator. So when that happens, we're going to go y equals, and it's going to be a ratio of the leading coefficients. So really I'm comparing 2x in the numerator to x in the denominator. In the numerator, that leading coefficient is that 2 that's multiplying with x. So I grab that for my numerator of my horizontal asymptote. And then when I'm looking at x in the denominator, that technically has a 1 out in front of it, so the leading coefficient would be a 1. So the ratio I get for my horizontal asymptote is 2 over 1, so we're seeing a horizontal asymptote at y equals positive 2. So in fact, let's take a look at that graph in Desmos so that we can see how these pieces come together. So 2x over x plus 1. So if we look at this graph here, what I can see is, let's see, our vertical asymptote was at x equals -1. So in fact, I can even graph that line there, x equals -1. So you can see how our function on the left-hand side is going up to positive infinity, on the right-hand side down to negative infinity. So we're not crossing that vertical line at x equals -1. And then if I graph y equals positive 2, we can see in the long run we're getting closer and closer to an output of 2. Like on the left-hand side, we're just above 2. And on the right-hand side, as x goes out to positive infinity, we're just below 2. So that's our long run behavior that we're approaching 2 as x goes to negative and positive infinity. All right, the second case here, we have x plus 2, so that has a degree of 1. In the denominator, we have x squared minus 1, so that's a degree of 2 coming from that x squared. So for the horizontal asymptote here, this is a case where the degree in the numerator is smaller than the degree of the denominator. So when we have that scenario, that's like our 1 over x case, or 1 over x squared. So that's going to be where our horizontal asymptote is y equals 0. All right, and then our last one here, we have x squared minus 3 in the numerator, so that's a degree of 2 from that x squared. 2x plus 1 in the denominator, that's an exponent of, or sorry, a degree of 1 coming from the denominator. So with this case, the horizontal asymptote, we have the case where the degree in the numerator is larger than the degree in the denominator, and that means we have no horizontal asymptote. And that would be done. So there are the different cases and how we find our vertical asymptotes and horizontal asymptotes.